PV source emulation is very important. When you are doing experimental work or even design work with circuits related to PV sources, you need to have a source which is stable and available all time of the day so that you can test your circuit, you can perform your experiments. And it should not be varying with the insolation dependent on the sunlight, clouds, rain and all those things in order for your circuit to function. Therefore, having a stable source whenever needed, any time of the day is very important if you have to do your experimentation and circuits and design with respect to the PV source. Therefore, we shall look at this problem and then see for the lab for you to work with a source which emulates a PV source as best as possible. We will try to demonstrate with a few circuit examples and see how you can go about building them. The simplest and the best way is to use a light source. So let us take, for example, a PV panel. Now let me consider this as a PV panel or a PV module. And this PV module is having two wires coming out of it, marked plus and minus, across which you connect the load. Now this PV module has to be excited with light to deliver power, and therefore we need to have some kind of an enclosure like this, and this enclosure is housing the bulbs. So this is enclosure, this is fan, so that the bulbs, when it become hot, you need to remove the hot air, and this enclosure is actually deriving power from 230 volts mains. And these are the bulbs which you see here, and these bulbs are energized to throw light upon the PV module so that it can deliver power. You can control the amount of light that falls on the PV module by controlling the intensity and the number of bulbs that are switched. So these light bulbs are bulbs that you can choose which has a spectrum as close to the sunlight as possible. Now each of the bulbs or a cluster of bulbs can have manual switches connected in this fashion, such that only those particular bulbs are energized. And the load is connected across the terminals of the PV panel in this fashion, and the load R0 is what you would like to drive. Now this is a very simple PV source, but unfortunately this needs a PV module, and the PV module output is dependent upon the area of exposure, which means if you want to go for very high powers, you need a very large real estate and then a large bulb cover area so that you can switch them on and off under your control. This is not such a feasible solution for very large powers. For very small powers and small experiments, this is fine. But once you start going to higher powers greater than 1 kilowatt, then you will have to look at other electrical solutions. Let us now see how we can go about emulating a PV source by electrical means. We take a simple DC source. It could be a laboratory power supply or it could be a battery. So let us say you take a battery and you connect in series a resistance. We will name this battery as VDC and we will name the resistor as RS. So this combination VDC and RS together in series form the simplest PV source emulator. Across these terminals you will get a voltage VT and the current through the terminals that will look like quite similar to a PV source. Let us connect now a load resistor across the terminals. Now I will call this load resistance R0, and we will make the load resistance a variable resistance so that it can be varied from 0 to infinity, or short circuit to open circuit. The voltage across the terminals, we will call that one as VT. And there is current that flows through the terminals through R0, and that we will call as the terminal current IT. Now if we look at this characteristic, IV characteristic, then we will see that the IV characteristic of this combination resembles that of a PV source, and therefore we can call this as a simple PV source emulator. So now let us draw the characteristics. Now x-axis, I will call the x-axis as VT, and for the y-axis I will have IT. Now I will set R0 to a very large value, R0 infinity, meaning open circuit. So which means there is no current flowing through the terminal. IT is 0. When IT is 0, now I am talking of a point on the x-axis alone. And what is VT? As there is no current flowing, there is no drop across RS, the whole VDC will come across the terminals, and therefore VT will be VDC if you open circuit the output. So I will put an operating point here, and I will call that one as VDC. So I have marked this operating point. Now at this VDC, the special thing here is that R0 is infinite. It's an open circuit. Next, I will short circuit. I will go to the other extreme of R0. I will short circuit the terminals. When you short circuit the terminals, VT becomes 0, which means then I am talking of a point on the y-axis. So I short circuit this, VT becomes 0. What is the current flowing through that? VDC by RS. So I will mark a point, another operating point, and the value of that is VDC by RS. And the important character of this operating point is that R0 is 0, short circuit. Now as you vary R0 between these two extremes, short circuit to open circuit, you will see a series of points coming up like this in a linear fashion. Now at the midway point here, I will mark, and I will call that one as VM, and likewise the midway point will be IM. So IM and VM. Why do I call it IM and VM? Because this is a linear one. At the midway point, you will see that the product VM into IM will be maximum, so power will be maximum here. The product here VM into IM is V into I is 0, because voltage here is 0 even though the current is VDC by RS. Here at this operating point, voltage is VDC, current is 0, and therefore you will get a triangular power curve P with the peak power operating point here. So this will be the peak power operating point. Now what is the fill factor? Fill factor is VM IM, this area, as you see here, this area divided by the total area as given by VOC into ISC. So if you see fill factor, which is equal to VM IM by VOC ISC. What is VM? VM is halfway point of the x-axis, VDC by 2. And what is IM? Halfway point on the y-axis, which is VDC by 2 RS, divided by VDC for VOC and VDC by RS for ISC. So if you work out, you have 1 by 2 and 1 by 2 coming appearing here. It is 0.25. The fill factor of this PV source emulator is 0.25. It is a very bad fill factor. Fill factors of PV panel should be of the order of 0.7 to 0.8 for a reasonably good PV panel. However, this PV source emulator is very simple and it will serve the purpose of doing experimentation at odd times, even at night, when you can get a steady PV source supply. This PV source emulator is very inefficient. Why is it inefficient? See, there is a current flowing through this IT, and always there will be IT square into RS drop, power loss. There is a IT into RS drop and IT square into RS power loss in this resistance, and that will make it pretty hot. Therefore, it is inefficient even though it is very simple emulator. So if it becomes hot there, you have to build in mechanisms where you will have to remove the temperature. So you may have to fix along with the resistance a forced cooling blower fan or something like that. So this becomes the PV source emulator, a very simple PV source emulator. Now we will look at this DC supply. I said we could use a battery, but using a battery is not convenient because the battery has to be always kept charged, and when it discharges you will have to find mechanisms or have another equipment to keep charging it and then keep the voltage at a nominal level. However, it would be very convenient if you get the power, draw the power for this DC power supply from a much more steady supply like the mains or the grid. Therefore, we would like to replace this VDC source by an electronic version of a DC generator or a DC source where power is drawn primarily, mainly from a grid or the mains supply. So how do we go about doing this? Let us shift this circuit this side. Now this is what I want to replace, so I will remove that, and instead of that VDC source we will be having some electronic circuit here which will link up there. We would like to draw power from the 230 volts grid, the AC mains. So let us draw transformer. It is not a transformer, it is an auto transformer. So we would like to have an auto transformer there so that you can draw variable voltage from the grid. And to that, let us interface a full bridge rectifier circuit. So this is a full bridge rectifier. You are familiar with this. And we will place a capacitor filter. A full bridge rectifier with capacitor filter output, and this will get connected to this point, and that will become the DC source. Now if you see, the portion of the system from here to here is what we will call as the PV source emulator. And this is a simple circuit. This is an auto transformer easily available in the lab. This is a bridge rectifier. You will get 4 bridge modules available in the market. You can buy them, put a capacitor across, and then you have your VDC. Put a series rheostat, you have your total PV source emulator. So this is a nice interesting circuit. You can use it any time of the day, and the load that you connect here can be used for testing a PV cell. So in the end, whatever experiment you have done, you will finally test it with the actual PV source, and if it works with this emulator, most likely it will work with the PV source. I will describe to you now a switched mode DC-DC converter based PV source emulator. You see, the previous circuit, which was simple and easily could be implemented, had one major drawback, that is that it was very inefficient, a lot of loss in that series resistance RS, and not only that, the quality of the IV characteristic was poor. It had only a fill factor of 0.5. But one major advantage with that previous circuit is that it was very simple, easy to implement. Now here I will try to describe to you in a block schematic form the operation of the DC-DC converter, switched mode DC-DC converter being used as a PV source emulator, such that the DC-DC converter output will have an IV characteristic similar to that of a PV cell. Now let me draw the block schematic of this switched mode DC-DC converter, which now behaves as a PV source emulator. It is supposed to be a current controlled converter, so the terminal current IT is supposed to be controlled. So therefore, I now have here with me a reference, IT reference, the terminal current reference, and a terminal current feedback. Now these two on comparison leads to an error signal, and this error signal is passed through a controller, which is a PI controller. And the output of the PI controller goes into a PWM block, and this PWM block is supplied with a triangle wave, and the output of that will be the duty cycle input to a DC-DC converter, like this. The DC-DC converter is supplied with VDC, and the output of the DC-DC converter is supposed to emulate the PV source, and that is connected to a load or not, like this. IT, as indicated here, is what we are supposed to control. So which means that I need to sense IT and then feed that back and get it controlled. So what this block diagram mainly indicates is that if I set a reference IT star, and the error here passing through the PI controller, PWM, DC-DC converter and all those things, and this current, terminal current being fed back in this fashion, the job of the PI controller is to make error 0, which means that IT will be same as IT star, which means IT is nothing but the terminal current flowing through the load, which will become same as IT star. Now that is a current controlled DC-DC converter. Now this basic topology is what we will use for making the PV source emulator. Now the DC-DC converter being switched is a very high efficiency converter, and therefore we will not have the loss as we saw in the earlier case or the earlier model. Let me mark the output voltage like this as VT, and let me also draw the VT versus IT characteristic like this. Now let us say this is the output characteristic that we expect across these terminals, the actual characteristic that we expect across the terminal that we would see. And this has a load R0, and therefore the load line, the 1 my R0 line, is like this with the operating point as shown here. So at that operating point we see operating voltage VT and IT. So So this is the actual value of Vt which you see here and the It which is flowing through this. Now let us sense Vt and use that Vt to provide the It reference. So what we do is have a lookup table of Vt versus It. And this lookup table is the one which we will be using to generate the reference for It. So you see that in the lookup table, Vt is provided as the input. It will check the independent axis and appropriately pick off the current It to be given out. So this It is given out and fed to the reference. So this way the setting for the It reference is done. Now imagine that R0 has changed, R0 has increased. So increasing R0 means the load line comes like this as shown in the green. Now the moment R0 has increased, It into R0 would be a higher value. So you will see that Vt is like this. Now that is the Vt, and what is actually expected as It is the horizontal. So this is supposed to be the expected It, but right now the It is here. R0 has changed. Vt has become this. Now we should try to see if the controller will bring back It here. Now let us see. Now this Vt has increased and that is given here, and which means it will try to look into the lookup table and see that the Vt falls there, and based on that Vt and intersection of the IV characteristic of the lookup table, you will get the new value of It, and this value of It will be fed as reference here. Now this is a lower value of It, and therefore this It will try to match this, and therefore this load It will try to match the new reference, and therefore come and settle at this point. So in this way, for any value of R0, this converter will track the It, and in that way give you a IV characteristic, and the IV characteristic as we have loaded into this lookup table. So this lookup table is crucial. The characteristic that you load into the lookup table is the one that will actually reflect here. So you can play around with the lookup table in terms of insulation, in terms of VOC, in terms of fill factors and all those things, and actually get a replica at the output at the higher power level. And this you can design it for any power level that you want.